So, starting with the median models, this is the biggest piece of driving the uncertainty in the hazard right now for the Arizona sources, or for the Arizona hazard model. So we began by a model selection. After workshop 2, we had limited or cut our model sets down to these sets of models: 1, 2, 3, 4, 5, 6, 7, 8, 10 models here. And then we are looking at the application of these models to the local sources for normal faulting events. Okay? So we're just doing one of these at a time, one of our four source classes. So we looked at which one should we be using. Okay, we want to have something that's going to address normal faulting effects because that's the dominant source type. So the Grazer and Calcom model, we have not used it. It has a distance attenuation bump in it that can be used to mimic a hanging wall effect, and it can get the attenuation from strike slip, but on the footwall it's going to put that same increase on the footwall side, which is not what we want for the host zone. So we have not used that. For Zhao's model, he doesn't have a normal style of faulting factor. You could add that style of faulting factor back into Zhao, but this is really our focus is on normals, so that and that is the dominant source type, so we have not used it there. For Zhao's modified model, his break in the magnitude scaling is higher than the magnitudes that are going to control the hazard, so that's not an important one to bring along. The ASC, BSSA, CB, and CY we have included as models that are capturing or have normal faulting terms and should be applicable to the magnitude and distance range for both the footwall and hanging wall sides. Idris's model we did not include. He didn't estimate a normal faulting style of faulting factor. We did ask him about that, which was described yesterday by Bob, and Idris said, well, that there could be a normal style of faulting factor, but he didn't think there was enough data from which to derive it. And then there's the 2 European models which have quite a bit more normal faulting data, and so we want to use those models as well. Okay, so there's 6 of the models that we're bringing along at this point. So Bob showed the logic tree structure that we're using for our normal faulting events here, and then we start with our evaluation data set. So there's an NGA West 2 data set. We're going to focus on magnitudes greater than 5, distances less than 70 from normal faulting events. So these are restricted subsets of the data applicable to our particular problem, but we're going to lose a lot of recordings, right? So it's going to be small data sets here. We're going to still have the GMPEs, which borrowed strength from all the other data, right? They used the scaling they got from strike slip and reverse and so forth, and the distance attenuation, so they knew how to control that and extrapolated it to cover the reverse, so that, or normal, so that's already there. But our comparison to data is going to be to this subset of data that is particularly applicable to us. We could have then alternative versions of those subsets based on which each developer talked about. Yusuf had mentioned that yesterday. We don't want to have just one set, for example, the ones that was used in the ASC model, because we want to see sets where data were rejected for one reason or another from other developers. There's also the European data set, so there's a resource data set, and then the source that use Acker's data set, which is very similar. And we're picking the same thing, a subset of those events, magnitude greater than 5 within 70 kilometers from normal faulting events. So we then are going to be using those models or those data sets as comparison in our Salmons maps. And remember, we're now going to take the 6 GMPEs and we're going to create 1,000. So you remember how that's done, right? We reparameterize each GMPE with a common functional form. Okay, once we have that common functional form, we build our covariance matrix for the coefficients. We then sample that covariance matrix to build up our 1,000 GMPEs, and then we can make our Salmons map. Other parts of the Median model, directivity, we're not applying that, which we'll be talking about tomorrow for Diablo Canyon. And so we're just using since we don't think that's an important feature in what the models are for background zones. For the aleatory variability part, we'll be talking about that in the afternoon, so I won't go into that in detail. We're just going to start to get through the median models. Okay, questions on that part? Steve?
Just to make sure, can you hear me okay?
No, it's on, you just need to put it close. Yeah.
All right, just to make sure I understand. You've got the first branch here on the logic tree is with respect to data set. Now, the same data has already gone into the generation of the GMPEs. Does that mean that these are the data sets that are going to inform how you partition the model space into these segments and sample them? How is that branch going to be used?
Yes, yes is the answer, and it could be affecting how you put the weights on the models. So what's not shown here is our set of candidates, models, in this case 6, and then going to 1,000, and then we collapse them down to 10. This is more of the structure of the logic tree as it gets handed off to the hazard analyst. They don't need to know how we got to those 10. They just know there's 10 models.
Right.
Okay? But we have a lot of stuff that we talked about yesterday going on before that. And we're going to talk about here how we're trying to do that part. Okay? So I'll show you where we're going on this and an example of putting those zones and how we're going to set the shapes and the approach for setting the shapes and how we would look at the range that could be spanned. Okay, so that's what this is all about. Tom.
So I'm sorry for this general statement, but we call it a logic tree. This is really a mixing model, and logic has if A or if not A, then B, and the totality of things have to equal 1. So for instance, we have all these models are various kinds of log normal distributions, and another model for logic's sake is not log normal distribution, but that's not in a logic tree. This is a mixing model, and at the end of the day, what we're really worried about is these very far from the normal in the distribution, the tails of the curve, and the logic tree doesn't really address that issue. But it gives when we say the word logic tree, it gives the impression that maybe it does, but it doesn't. So we should just call them a mixing model.
You're taking on decades of past precedent of what these things are called. The only place that, the numbers sum to 1 are what the weights are. I would agree to you, they're not necessarily probabilities. They're weights that we're assigning to the credibility of the models. But it's the field has been using this term for this kind of a structure for too long for us to change that now. But I
understand that, but the NRC said think outside the box, and really we ought to, if we're going to use the word logic, we ought to be logical.
So I'm hoping this is logical, or at least organized and in a logical format in terms of how we're trying to address the alternative models.
So in that case, if we're going to do that, one of the branches ought to be non-Gaussian.
Yes.
In some way. And whether it's at the long period end or it's at the very high frequency end from these slap downs, one of the branches in here should be something that's not this group.
Correct. So we do. That's what we're calling that our fat tail model, where it's deviating from a log normal distribution.
And where is that in here?
where will we put that in here, Bob? I guess it,
We have two branches displayed up there, which would be, right now, are nominally called magnitude independent or magnitude dependent. They could be, I mean, they would be there. Right now, we're actually possibly envision that it will always be fat tail.
right. Our current approach is a fat tail model is the way it behaves with certainty as opposed to a log normal with certainty. I think that's what Bob is saying is our default model right now. But we can have a branch in there, and that's something we need to talk about. If we want to bring along the fault normal, or excuse me, the log normal all the way through and have an alternative of the fat tail model. But what you'll see this afternoon is we see evidence for the fat tail, and that should be our base model as opposed to an alternative.
I could make you some distributions based on fat tails, log uniform distributions in long periods for the very high frequencies for slap down. I'm not sure how to do that, but I'm virtually certain it's not going to look like any kind of log normal distribution if we seriously tried to do it.
Okay. Any other questions about this part? I think it would be useful, Bob, even to structure this with a log normal and then a fat tail branch. And even if we zero out the log normal and just use fat tail, that would be fine. But we should have it here, I think, to keep track of it. Okay, any other questions? All right, issues for our ground motion model for Arizona. One is magnitude distance scaling, and basic assumption here is that the range is going to be captured already by the 6 models. So the magnitude and distance scaling is already adequate, and our focus is going to be on the normal style fault or faulting factors and what is their uncertainty. That's going to be the biggest piece that we have don't have good constraints on. So if we look at just an example of the data from, this is Bohr, the BSSA model. On the left-hand side is magnitude versus rupture distance, or excuse me, joiner bore distance, and the blue dots are the normal faulting events. So there's not a lot, right? This has been our problem is we have mostly strike, slip, and reverse events in the NJA data set. We only have a handful of earthquakes over magnitude 5 from normal faulting that we can use. At 10 seconds, this problem is worse, but we understand that. If you just look at the number of normal faulting earthquakes used in the GMPEs, I didn't include Bindi. I didn't have that data broken up or counted, but you can see for the NJA data set, there's really a small number of normal faulting events. So in each of these magnitude bins, there's 1 or maybe up to 5 earthquakes, whereas the orange one is the European data set, which has got, here 34 earthquakes, while we may have 4 earthquakes in our size for that magnitude range. So there's a whole lot more data or earthquakes to use from the European data set, but most of those earthquakes have only 1 or 2 recordings. So that makes it difficult for us to get the event terms out, or reliable event terms. So that's going to be the trade-off here. Lots of earthquakes, but most of them sparsely recorded. Okay? So which would you rather have? Is going to be the question. All right. This is what the normal faulting factors look like in the GMPEs, so in the 6 models that are there. So these are the ratios between strike slip and normal. Okay? So, and these are, so if it's minus 0.2, that means the normal ground motion is 20% lower than the strike slip motion for that same magnitude and distance. Okay? So there's a wide range of what these numbers are between the GMPEs, ranging somewhere between 0 to minus 0.3. Okay? So the large uncertainty there is reflected to having a small number of earthquakes to use in the NGA West data set for normal. For the European data that's up near the top, the numbers are closer to 0 or minus 0.1. But again, We're getting those from an average using a whole lot of poorly recorded earthquakes instead of a small number of well-recorded earthquakes. Okay? So this is going to tell you large uncertainty in the normal faulting factor. The NGA models are calibrated on strike slip and reverse. Right? The normal term just comes along at the end, and so the uncertainty in the normal ground motion is driven by the uncertainty in the normal faulting factor, here ranging by up to 0.3 natural log units. The European data has a lot more normal faulting data in it, so it doesn't have the same issue of being a strike slip model with another factor added on to get it. There's enough data to really be controlling the normal faulting part of the equation. It's normal and strike slip. They have very little reverse data. If you were trying to do a reverse model, you'd have the problem we have trying to do a normal model. Okay? So that's helpful for them. So their medians are somewhat different in that even if their normal faulting factors are smaller here, there could be differences in the strike slip ground motion as well, and we need to have those things combined. Okay? But this is really giving you an idea of sort of an uncertainty that's going to be coming along on top of our models when we try to predict normal faulting from a strike slip based model, which is what these 4 NGA models are doing. Okay? Three. So they have more small magnitude data, not a lot. So there's a problem, right? Lack of data, and how are we going to deal with the uncertainty? Okay, so I'll just run through some of the data. So for CB14, the CY14, and ASK14 models, we had the event terms handy. I didn't have the BSSA ones yet handy, but I'll show you what they look like. The event terms relative to strike slip, and what that means is I took the event term, but then I also put in the difference between normal and strike slip so that we're looking at what would have been the event term for the normal events if I calculated the residuals with respect to the strike slip model. Okay? And then the line going across there is what is built into that GMPE for the normal faulting factor. We don't fit data like this, but it's a way to try to interpret what's going on. Those would be the event terms without a normal faulting factor in the regression, and then the line is, it could be interpreted as what our normal faulting factor is. Okay? So there's a whole lot of data there, it's a big scatter. We really care about what's going on here, and what Yusef is mentioning, there's very few data that we're trying to use, large magnitude normal faulting events to help us out. So here, this model has as a normal faulting factor of minus 0.1 natural log unit. The vertical axis would be the event term relative to a strike slip model. Okay? So if it was, and the blue line is where I would have said 0 is in my GMPE because I used the minus 0.1, okay? So we can get these, but you're going to see they're not always going to be mean-centered, and this is what we talked about. There's a whole lot of smoothing that's been done, going through these, not fitting these data precisely, right, as we move along. Cho and Young's and the data sets will change depending on what data set were selected. That's their model. They have a negative 0.25, so a larger difference between normal and revert and strike slip, a larger reduction. But you can see we're really looking at here these 5 events. Sorry. I'm like Christine, I'm not used to be told to talk louder, but I will. Next one, Campbell and Besorgnia, same thing. They have about a minus 0.2 for the style of faulting factor for normal, and you can see the data, and these are the event terms, so these are consistent there. Okay, but we're still fitting a sparse number of points trying to get at these effects. If we just put all of those, and on top of this has the Bindi model and the Acker model, and Nick, we forgot to put Bohr's model on these curves, so we probably should have done that. They have a minus about 0.2 in this range here, so about the same as what these lines are. And I just put all of the points on there, even though they're from the same earthquake, or they may represent the same earthquake in different studies. You can see how the points are moving around based on what the regression analysis is doing. Okay? So there's a lot of different things. Partly, if you put in a depth effect, and these are deeper, then that takes out some of the effects that might be mapped into a normal faulting factor if you didn't have a depth scaling. So there's trade-offs that are going on, which is causing the points, the event terms, to move around between the different developers. Okay? What we're trying to really get, though, out of this is the range of what these are. And then I'll do the same thing for half a second. Okay, so for
Norm?
Yes, it's half a,
Why wasn't the BSSA model included here?
just because we didn't have the residuals in the timing
At that point, okay. all right.
to make this.
So you didn't,
We-
okay, all right.
Now-
Just wanted to make sure you hadn't excluded it.
No,
for-
no, and it's back here, so you can see where it
Yeah,
will be.
right, it
They
was
have
there.
an unsmooth style of faulting factor that this is what comes through. So in the PGA, it's about minus 0.25. We'll look at 2 seconds where it's about minus 0.15.
And,
Steve.
Norm, you mentioned some of the factors that make the residuals bounce around, but can you give some explanation or some hints about what's driving the lack of mean centering of these things? What are some of the considerations that have led these to not be mean centered?
So I can talk about my model up here. So it's sitting in these light orange points coming across. In the first regressions that I did, I was getting numbers closer to what these guys were getting. Very large negative numbers, but not very robust, controlled by a couple of earthquakes. And if I changed the sampling of events, that number was, that style of faulting factor was changing significantly. So it hasn't been very robust. So what I did is I limited the effect of it and said I'm just not going to go below 0.1 in that particular case in this short periods. That's closer to what we'd had previously. And so really it comes down to saying I don't want to try to match these, because then that maps itself into other features of what the scaling is. So it then starts to fight the other parts that I think are more robust. So this is the phase where we're taking what we think is the way things work and not having large, deviations. Let's say I don't want to make it go from 0.2 down to 0.3, even though that feature is something you can see depending on a subset of the data. If you have particular 8 events, they may show that kind of a feature. So this is these are the cases where we say we're not going to let the sparse data control the model, even though you would get a better fit if you followed those data precisely.
Is it roughly correct to say that the bias is to damp these terms towards 0?
Yes.
Thank you.
I don't know if Bob or Brian, what you guys did on your normal faulting factors.
We were getting numbers that were, I think, significantly lower than the smaller or more negative than we were getting in 2008, and with less information because of the somewhat reduced data set for normal. So we just kept the 2008 numbers, feeling that we didn't have enough data to make it lower than it was in 2008.
So I guess I'd say that bias is still towards a 0 effect as opposed to a very strong effect. And Youssef, you need to use a microphone. Or do you want to answer that?
I was saying that we examined these things. There's one.
You put it
there
closer
is
to your mouth. There you go.
There is one important earthquake that dominates that reduction, and that's local. So you have to be careful, as you just
Right.
said. If you just close your eyes, you get huge minus here.
Yeah.
Yeah. And you can see in that plot you did, you didn't identify events, but L'Aquila is sort of an outlier in our, probably in everyone's.
Yeah.
But the data, as far as the CB model, the data was allowed to fit that term. As you can see, it looks centered.
Right.
Okay. And what we found was there was a trade-off. There is a depth term in there for all mechanisms. We didn't see a difference between mechanisms. But that definitely traded off with the factor. So I think without depth, that factor wants to be smaller, which might be why the Europeans get smaller numbers at this point.
With no depth scaling in the models as well.
That's hypocentral or
Paul?
detour depth, yeah,
Right.
just to be clear.
Paul?
It seems there's a lot more scatter in the event terms in the ACAR model than in the NGA models.
I didn't show you Akamar. This
Yeah,
is
that
my
one.
model. So ask is me, so I have more scatter. This has class 2 events in it, and that's part of what has been pushed, one of the discussions we've had, and different depth scaling. So this was I had a really hard time on the normal faulting terms. So letting them do what they want, constraining the depth scaling first, then deriving what's left, and in the end, a bias towards a number closer to 0. I think that's a fair way to put it. So when we start to look at the salmons maps and the data, keep that in mind, and you'll start to see what we've been talking about, okay?
Could you say again where the horizontal line comes from?
That's the horizontal line is the mean normal faulting factor in the GMPE. That's the term in the GMP. So they would say. Did you get them? Okay. Yeah, cut off. That's it. They get one time and then they're cut off for good. So they should be centered about that value. Okay. If the data we're controlling, and we don't let that really happen all the time. So we force some smoothing, and then that gets back into the mean of the model, and really a small adjustment happens with the mean from all the other events, but there's so many more of them, the model doesn't change very much. Okay.
Unmuted. Norm, this is Robin. Can you hear me?
Yes.
Yes. Question on these factors. Has anybody tried to calculate a confidence interval on a normal faulting factor accounting for the correlation among records coming from the same event? It just looks to me like your factor there would not be statistically significant.
We're going to mute you again, Robin, and I'll answer the question. So that was one of the questions we asked the developers during workshop 2. What's the uncertainty in your normal faulting factor? The uncertainty came out to be somewhere around 0.1 or so natural log units. So you could say here it's not very, may not be statistically significant. If we had let it do what it wanted, for example, if we went to the, I should show here, the BSSA model, they would have, again, about a 0.1 standard error on what that term is based on the number of recordings available. So, yes, we've looked at those confidence intervals, and Robin, because we're using event terms, they've already addressed the correlation of recordings for multiple recordings in an earthquake. So that's there. When we have only 1 or 2 recordings from an event, then that average residual is partitioned partly into the within event term and partly to the between event term. So these things aren't very robust until you get, we like to have 5 or more recordings per earthquake to start to get an event term that you can trust. Tom?
Unmuted.
When we talk about statistical significance, it's only in the earth sciences that we have in, in practice that we look at a data set, form a hypothesis, and then ask statistical significance of the hypothesis. In other fields, it's required that some experiment be run after the hypothesis is done, some sort of double-blind predictive testing. It's well known in statistics that if you look at a data set, you'll see some pattern, ask if it's significant. Of course it is. But it's not a real test of statistical significance. So there's really no way we can do this problem except wait for more normal fault events. I mean,
the other part of what we're trying to do is to capture the range of allowable answers, which is different than saying, is this statistically significant? It's almost the other thing. Can you tell me I can't be this high, or I can't be this low, as opposed to here's the fewest number of parameters to match the data.
Well, so when we see patterns, we can ask, is the pattern look obvious? But we can never assess statistical significance without doing a predictive test because there's always bias
in what's going on
in the test.
All right, let me try to move on. I was thinking this would go, I wouldn't have enough to show you, but that's not our problem. Nico, do you have those plots, by the way? Not yet, okay. I want to see his fitting of the normal equations, yeah. Okay, this is just throwing it all together again for the 2-second value, okay? So the numbers are smaller in general, clustered around 0. Some are, one of the European models, Bindi, has a positive event or style of faulting factor, so plus 0.1. The others are generally minus 0.1 to minus 0.2. Okay, so Nico takes these 6 models and he fits them to the common parametric form. We're using RJB as a simple way to account for hanging wall and footwall effects in a background zone without having to deal with the details of the hanging wall model. So Youssef is going to speak into a microphone.
So for normal, he's switching. Nico is switching to RJB.
Yes.
Okay.
And for the reason is the application. For the what we talked about yesterday, one of our issues was, especially on the hanging wall, we probably want to do it both ways because of that's a significant difference, and hanging wall effects are important to us. Here in the background zone, it's not as of a critical issue, but we want to capture it at least through the joiner bore distance metric. So Youssef is shaking his head yes and no for those of you online, or yes, he's shaking his head yes, I should say. Yes and no. Sorry about that. All right. Any questions so far? You remember what we're doing, Brian?
So you're going to show us how effective the RJB's capability to capture hanging wall effect later.
We would show it's not its ability to capture its ability to fit the data on both sides of the fault. Right. And so because Nico is running minus 70 to Rx of minus 70 to plus 70, okay, so we have both hanging wall and footwall, and then we're just fitting those within RJB distance metric.
So with the RJB distance, that functional phone is able to fit the hanging wall as well as the fit to the footwall. Is that?
It smooths through it by definite, the way the short answer, yes, because the joiner bore distance metric brings along part of that. We've seen previously with dipping faults of around 45 degrees, magnitudes in the sort of 6.5 range. We got similar hanging wall scaling for the RJB metric as for when we use rupture distance with a hanging wall term.
Okay.
If you went to much larger, 7.5s, it didn't work, or really low dip angles, it didn't work. But for this application, it should be adequate.
Okay.
And we need to show you, and that's what Nico is working on as we speak, okay? Okay?
One other point, unrelated, but we also, as a part of Linda and our assessment of epistemic uncertainty in the basic models, we have larger numbers for normal faulting events from NGA. So
Larger epistemic uncertainty.
larger
yeah.
epistemic uncertainty.
How large are those?
It goes up by 0.03 from 0.08, so about 30%, about 40% higher.
But the number is 0.12 or something like that, 0.11.
0.08 versus to 0.083 to 0.12, 15 or something like that.
But if we went all the way back to here, we also already have a really big range in what those factors are. Okay, so Bob is getting to almost answering our ability to estimate that factor, if you believe where the model is, puts on an additional variability or uncertainty. All right, let's see where we go. So for our data sets, and we're going to show the one for the NGA West 2. So it's, again, using the ASK selection. So it has a bigger set, or class 1 and class 2 in there. Magnitudes greater than 5. Distances less than 70. And a VS30 greater than 200. Then they were, or 250, they're corrected to 760. Part of this was so that we weren't doing too big of a correction on the VS scaling. We may want to relax that and let a few more go down to 200 meters per second to try to build up a few more recordings. When you do that, you get 51 recordings from 7 earthquakes. Not a lot to work with, okay? But at least these now all have at least 3 recordings per event. That was one of the criteria I had in my data selection. The European data that we're not going to show you the Salmons maps for, but we need to make them and do the same thing. Either the resource data set or what Akar used, which is similar. So the resource subset. Well, he actually has more recordings. So, let's step back. We looked at a subset of the resource data for greater than 400 meters per second. So they're a little bit different. That's what Nico was starting with. And there's 140 recordings from 50 earthquakes. So you have an average of, say, 3 recordings per event. Akar's data set, if I went all the way down to 250 meters per second, had 187 recordings from 55 events. If I did it for all of the data, then there's another 20 or 30 recordings less than 250 meters per second. Ken, did you want to say something?
Yeah, I was just going to say, Akar et al. Used a subset of the resource database, but the largest number of events that he removed didn't have VS30s. That's why. And here, I presume for the resource database, you're only using data with VS30 values.
Correct.
Right. So this is why you're getting,
That.
I think this explains the difference you're getting. If you went down to 250 for the resource database, you'd probably get almost the same number of recordings in earthquake.
And then if you go a little bit for larger magnitude, then it's going to be reversed. So number of earthquakes and recordings in NGA, I assume, will be larger than European.
Or almost the same. I mean, the normal faulting data sets, we don't have a lot. I guess we have some Chinese data, right, is the stuff that's outside. But
I was curious if you go to 6, whatever.
Okay. Yeah, but we haven't broken it into a higher magnitude. We start around. So what do the maps look like? So the region is outlined is what's sampled by the 1,000 realizations. Okay, so all the gray points aren't shown on here. What's shown on the red points are the GMPEs. Okay, so I hope you can see them now. So Bohr up there, Campbell and Bezorgnia, Cho and Young's, Bindi, Akar, and the ASK model. What's shown behind this is using the NGA data set, those 7 earthquakes, 50 so recordings, or 150 recordings, excuse me. No, 7 earthquakes from 50 recordings. The mean event term. So that's one way of looking at what the mean bias would have been of the model to predict this subset of the data. Right? And that's evaluated at every one of those 1,000 models, and then the contour is put on top.
I'm not sure, because you're looking at normal faulting effect. Right? Oh, are you also plotting something else? Because
This is not normal faulting effect. This is normal faulting ground motion models.
So okay. So you're looking at a scalar, or you're looking at a vector here?
A vector.
Okay, so what is the vector?
The vector is ground motion, magnitudes 5 to 7, correct me, Nico? Distances 1 out to 70 kilometers, 50 kilometers. 1 to 50 kilometers sampling. And then we have this, in this case, 1 period. And we went positive and negative on the, did you run positive and negative RX?
Okay, so this is, you're still showing the prediction from the GMPEs. Are you showing event turn or showing the prediction?
So the points.
Okay.
Okay, so we take each model, we parameterize it, we create our 1,000 models. Okay? For normal faulting only.
Yeah.
Okay? We're fine there, right?
Right.
Then he's going to fill up a vector of forward predictions from each of the 1,000 models.
Right. Just like what he showed.
Yes,
yesterday.
this is the same thing as yesterday.
Okay, the plot set mean event term. What does that mean?
That's what's contoured in the background. The shading. Remember the salmon? I couldn't quite hear you, Christine.
I think you're in the right direction to remind everybody where we're going.
Okay.
Just keep on going and get to this.
Let's remember what we did, all right? So I don't have all the same pieces, so you need to remember from yesterday what we were doing. We created the 1,000 models. You could imagine there's 1,000 gray points, and they map out the space that's highlighted here. Okay? Ignore the coloring in the background and ignore the title. All right? That's our salmons map for the 6 GMPEs in the space created by the 1,000 realizations. That part's good. Now go to the background. So if you remember yesterday, what Nico also said is we can, at each one of those GMPEs, you can go to the data set and compute the event terms. Compute the residuals. So he gets an event term and a residual for each of the 1,000 GMPEs, one at a time. He keeps the standard deviation, the phi and the tau fixed, okay, and so that those are fixed at standard numbers, so that we're able to see where we don't want the phi and the tau blowing up and then getting event terms going all off because of the large standard deviations. We have some confidence in what the standard deviations need to be. We can't have phis of 1 and we can't have taus of 0.8 or something like that, okay? So for each one, we're going to get a set of residuals. I will have then 7 event terms for the 7 earthquakes. I'm going to take the mean of those. Okay? Because we assume their mean is 0. It's like the C0 term if you want to think of it as the constant. And then we make a contour plot of what that mean event term is for each one of them. So that's what we showed yesterday afternoon. Nico also showed you the likelihood. So it's the same thing that contours of the likelihood evaluated at each of the 1,000 models from this data set. So for this subset of data that we selected, what would be the likelihood these models created or our selected data?
On this likelihood plot, does it include the mean event terms from the previous plot for the NGA West 2 models?
It should, yes. It's the likelihood calculated with an assumption that the mean of the event terms is supposed to be 0. The mean of the within event terms are 0 in calculating the likelihood. So the further you get off from that, the likelihood goes down. And we didn't let the fees and the taus blow up, so that that forces a steeper edge on the likelihood plots, so that you don't get what looks like a higher likelihood just because you got a really large standard deviation, right? So, and I think that's the right way to inform ourselves on what the median models are. So we don't get out here and say, oh, I can still get a high likelihood out here, but I'm now using a phi of 0.9 and a tau of 0.8. Okay.
Norm, this is Robin.
Yes.
I think it would help understanding if you explain the x and y axes, why one has a range of 8 and the other has a range of 30, and how each ground motion equation plots on those axes.
There's no short answer to that. And the best thing is don't pay attention to them. What you should pay attention to is what's in the background. Okay, the background, I don't want to tell you, I can't show you that yet. That's too soon. The background here, Robin, is telling you each one of these contours is 0.2 natural log units. So you can see as you move from one to the next, the median ground motion, the model is moving by 0.2 units. It's getting larger as you go from right to left. So this would be near 0, then I'm 0.2 units high. So if I had a scaled background approach, I just took my GMP or bumped it up by 20%, I'd move it over about this much to the left. But I think that...
I understand that, Norm. I understand that part. But what I don't understand is when you say ignore the background, and then you go on with the next...
I'm trying to tell them how they get here, because remember, these points are this high dimensional space projected onto a 2D map. Okay, and repeatedly we've been told the coordinates and their positions are not what's important. It's their relative distances, and then to add some physical understanding to it, we put these other things behind it so that you can understand what it means. Okay, as I go from one edge of the map over here to this edge of the map over there, I'm looking at e to the 1.6, so a factor of 5 in the ground motion model. That's a huge difference. But that's why we're putting this stuff on the background, so you can start to see something and have an idea of an interpretation of what a distance means in this space. You can also see going vertically, there's almost no change. What that means is there's a lot of different ways you can model this data and get a mean of 0. You could change the magnitude scaling and adjust the distance scaling and get sets that are going to be different in their GMPE space, but equally well fit the data. This is telling you things trade off. If it didn't, then we'd have a nice bullseye here, and you have to be in a certain area. Youssef.
Norm, so two of them fall in positive?
2 are on the positive side. That's the European models. See, something's coming up here, right? So those are the models that had the most normal faulting data to work with, and they're coming up a bit higher. Okay, the other ones as we move over are going more negative. So remember, these guys both had about a minus 0.25, I think, right? So that's why they're showing up on that side. Now, when we start to think what's allowable here, remember the uncertainty in what the range is going to be. The NGA models are basically strike slip models constrained with a factor added onto it, which may be between 0 and minus 0.3 from what we've been looking at. Okay, so that gives you an idea of how far I could have been moving these things around and still be matching the data. If you looked at the likelihood plot, you see how flat the likelihood is. And where is it flat? It's flat to the left, to the lower ground motion, or the lower effect, right? And so we're going to be seeing over here, this is moving to a different part of the ground motion model. Sorry, these are going up to higher ground motions as we go to the left, which is driving that style of faulting factor to 0. And it's still allowable. Doesn't mean that's what we want to do because you had other interpretations going on in what you did, but that's the way we make sense out of all of this stuff. Okay? We can't go very farther this way. We're falling off the cliff on the likelihood. Those models are, given this subset of the data, those models are at the edge of what it wants to have. Now, if I had chosen your exact subset, Yusuf, it may have been a little broader, moved over to the right. Okay, but that's the way we can start to get something out of this stuff and interpret how do we build our uncertainty model that's going to capture what is the range of the GMPEs that could work, that we need to consider. Is that making sense to people?
Can you
Norm, I
go
have
back to the previous slide? So Yang has a factor of minus 0.255, but on that map it's less than 0.2, so
Different data sets. Remember, this is my
Okay.
data subset, so it's going to be a little bit different. If I plotted this with your data subset, it should fall on that number. I mean, you should fall on actually, if you did it mean-centered, it would be 0. If you biased it a little towards 0, then you would have a bias in there.
Okay.
But you also can't look at this plot as, and just think about the style of faulting factor, because the style of faulting factor is relative to the strike slip model, which
Right.
could be higher than the other
Right.
ones.
This has everything
This
in
is
it.
the prediction of normal faulting earthquakes.
So what GMPE you use for generate? I mean, when you sample, when you fit the GMPE, do you have a normal faulting terms in it?
Yes,
Yes.
it's only the normal faulting GMPE. That's the only way we applied it in the forward way. You must use the microphone.
So Norm, that's why Nico is going to run for different databases. I mean,
Yes.
selected databases.
Right. So
Not
we
just different databases, but different parts of the
Subset,
model. This
subset.
one is only
Selected.
parameterizing the normal part of the model.
but for this zone, that's
Yes.
all we need.
Yes, just
Okay.
clarifying. Yeah.
So we have 4 source categories, source classes, I think we've called them, right? And in Arizona, there's 2. Normal faulting in the close by, strike slip faulting at large distances. Tom, can you get...
What makes you think that the Arizona case is normal faulting for the close by?
That's what the source characterization is giving us.
But when we go to these areas, they're almost always transpressional. They're strike slip almost always in these transpressional environments. I mean, sometimes it's easier to see the normal scarps, but I mean, frankly, it'd be shocking if it was only normal faulting in Arizona.
Right. So I have to kind of just tell you, Tom, not our scope, okay, unfortunately. Tom Rockwell maybe can help you out or talk to you a little bit about the constraints. I don't know how good or the basis for that part of the model, But what we're given is this is a normal faulting source, and so we have to generate models for the earthquakes that are made by the source people. Gabe is trying to answer you, I think. Hold on.
Yeah, Tom, I can address that. This is Ross Hartleb. I'm the project manager for the Palo Verde SSC. And the base case that's being described today for the Palo Verde SSC is exactly that. It's the base case model. We're slightly behind the GMC in terms of the shack schedule. We've not yet had our workshop 3. So we are still constructing our preliminary SSC model. And our workshop 3 is in late April. What you'll see in late April is probably for the host zone, we will have a mix of both normal faulting and strike slip earthquakes in the host zone. More heavily weighted likely towards normal faulting, but we will allow some strike slip events as well.
So you need to let us know that, because then we have to build that model. So sooner rather than later, and if you think you're going to have a strike slip case, you should just say we're going to have one, then we'll build the model to work for it. So
I will tell you right now, we will have a strike slip case.
All right, so we need to add another zone in here. Either we do a single model with a style of faulting factor, or we do a separate one for strike slip, and we'll have to talk that through. But let's keep working on this piece, and then we can go forward. Linda.
I have a question. Maybe this was covered yesterday, but I didn't get it completely. So you just said that there is trade-off in magnitude scaling and other things, that you could have other functional form that would give you the same likelihood, right? Is that what you meant?
Yeah, it's not functional form, but sets of coefficients.
Not functional form.
So these are all one functional form.
I know, but
I could put in different coefficients where I'm trading off on the magnitude or distance scaling, and equally well fit the data.
Okay, I thought it was different functional form. Then it's fine.
Okay.
No, do you have, for example, for 2 seconds that it should go close to 0? I assume.
2 seconds. So 0 line is where is 0? Right there. And the models are piled up on 0. So, see, yeah, okay, it must be working. Youssef is already anticipating the results. So, Linda.
So if you were to use different functional form, how would that look like? I mean, is this additional epistemic uncertainty, or it's
we think it would just overlay this one.
Okay.
So I can use a different functional form. I can take the Cho and Young's form that Brian has recommended and create the same a map like that. Okay, and then these things we could, if we evaluated them at the same vector of coefficients, there should be a strong overlap between those models, because you're still fitting the basic data. The differences would be if we had a real change, some fundamental difference in how the whole scaling works. But if we looked at any of the forms used in the 6 GMPEs here, we could have set those as the basis and derived the rest of the models in that form. Remember, we use a common functional form so that we can get the coefficients and that they're comparable and develop a covariance matrix for the coefficients. Otherwise, we're stuck. You go to the non-parametric model that Nico wants to go to, but that introduces a whole nother level of difficulties. Okay. Go ahead, Brian. You don't. The time is fine, because I've just got, these are my slides, and I have some interpretation on top of that, but let's first make sure you're comfortable with this piece of it.
Okay, I'm still trying to figure out how to interpret this map. So the fact that for the PGA map, Cho and Young's style faulting factors for normal faulting is not 0.25. You said it's because the number has been re-estimated using a different data set.
I never said
No.
that. No. Why don't you try to explain them to your
We
co-author?
take it's not plotting style of faulting. It's plotting our predicted ground motion model. So he took CY14 with the style of faulting term and fit the ground motion, fit the parameters to it, and then predicted this data. So the style of faulting term is only one part of the model. So you cannot just look at that map and the first map on PGA and see style of faulting terms there, because it's style of faulting relative to the strike slip model.
And the strike slip models could
And the
be
strike slip
different.
models are not all in the same place. If he had done this calculation where he had fit the strike slip models and then used the normal faulting data, then you would see everything would move around, and then the locations would be more in line with perhaps the normal faulting terms. So the location on this map has got two things in it. It's got the style of faulting term and where the strike slip model is relative to each other. So it's not just style of faulting terms on this map to show the differences.
You don't look happy, Brian, but this is...
Yeah, I just trying to figure out what goes into the calculation so I can properly interpret the results.
So this is a normal ground motion model. Everything that you need to compute the ground motions for a normal earthquake are there. The magnitude and the distance and the depth and the style of faulting, all of that goes in there. So style of faulting is one term out of a whole bunch that describe the characteristics of the ground motion. So if we have depth, hypercentral depth, that's in there. So differences in hypercentral depth scaling or Z-Tor scaling are showing up on this map. The constants and the banding gives you some idea of how much those normal faulting ground motion models are different from each other in an average sense. If I was to just say, I'll take CYO 14 and I'll add 0.2 magnitude 2 natural log units and make a new model, it would kind of get yanked over this direction. Because this is the direction in this map of a constant shift. If you remember at workshop 2, Nico had put on there, here's how, if we change magnitude scaling, here's the direction it's going. If we change distance scaling, here's the direction. If we're changing constants, here's the direction. These maps are simple enough that you can tell the constant is going this way. Magnitude scaling or distance scaling would be other directions on this map. So when we're going this way, we're picking up different magnitude and distance or depth scaling, whatever the key factors, that all are leading to about the same mean residual from the data. But they have different features, and that's why we don't want to just take a model as a backbone and move it this way. We need to capture the space in the other dimensions, in the other directions. Move on. Okay, Brian. Get my zones. Yeah, John. Almost to the zones.
If the models had not plotted over a fairly wide range, which they do actually, in this space, they're in the vertical direction, they're plotting over a pretty wide range. If that had not been the case, suppose they were clustered below, would that be a concern, and then you would want to perhaps use one of those 1,000 models that was higher up to sort of capture a broader range?
Yeah, in fact, we still are going to be looking at using those 1,000 models because there's holes here that aren't captured. Should they be? Okay. So if they had all clumped together, maybe we would have had to add the epistemic uncertainty to those models beforehand so that we generate in a broader suite. But this big range here is just this space is the whole space that Nico gets by assuming the coefficients are normally distributed variates, right? Correlated variates, and just cranks out a new set. When we do that, part of what we've talked about out on these edges, you're probably making models that don't make sense. Because we haven't gone in and applied any constraints to say, it must go, scaling with magnitude or distance must behave this direction.
Was there any other model that you excluded? Now you can put it back to see where they are?
This one, the table?
Yeah. Then if you put it, yeah. So for example, if you put, I just want to see, you excluded to begin with, then you put it back to see really the exclusion was minimal.
We haven't done that.
Okay.
So we could plot them back on that map at that point. A question, though, what do we do with it is another issue. But yes, you could stick them back on there. Okay. And Nico's probably almost done with his plots, or no, he's shaking his head. No, okay. It's going to be after the break. Okay, so what do we do with this? So there's a couple of features. So this is where we kind of stopped yesterday and said, all right, we can make this map. We can talk about this is the space of ground motion models that we can now talk about carving up and sampling that space. Whether we sample it with one of the 1,000 models or one of the original models, those are options to talk about. But how should you be carving up this space? So one approach was what Brian had said, you could simply say, yes, these are all your models. The space that comes out, you use the centering of where these models are and its distribution. Yeah. By itself, the density functions of those 1,000 models to describe it. The other point is now we have something subjective, though, as well. We start to understand, okay, the Bindi and the Acker and Balmer models have more normal faulting data. They don't have as much large magnitude data on which to help guide the rest of the model behavior. Those are two different things. Where should we be centering it, and what should the shapes be? So my first thing of looking at this is these contours are elongated in one direction. And if I look at the likelihood function, it's also something drawn like this, right? So given this subset, so we're using the data twice, we've already talked about that, but it's fitting this subset, there's a range of models that are all going to fit about equally well. So my first approach to this is to say my zone should be elongated, in this case, in the y direction, because those are giving me I'm picking up changes in the median means, which are behind there, and that's the way my likelihood function is also elongated. Okay? Instead of using circles, I'm going to now stretch it out and use an ellipse.
That makes sense, but in fact, I thought that even more you want to go.
You could elongate it even more. But remember, I'm trying to capture, as I go this direction, same bias, same fit to the data, but they're actually different. Right? There are differences in the functional form or the magnitude and distance scaling. So you don't want to ignore all of that, or you're just going to be saying, I'm just only worried about the constant shift. So this was my first cut at trying to do this. Where do you center it, and how do you elongate it or shape? Go ahead, Christine.
So Norm, this is here focusing on, normal events and all that. But when you're going to put weights, are you going to further segregate and maybe have subsets of magnitudes? And I'm seeing what we're doing here, but how are we going to combine all those different things?
We're going to put weights on the GMPE. GMPEs.
Yes.
That applies to all of the magnitudes and distances for which we are going to use it.
Okay, but will you do this exercise globally or by subsets in fitting these data? Like here, we're focusing on one.
We will do
Okay.
alternative data sets
Okay.
behind there to see if that's telling me I should be moving differently or if it's consistent. But I don't want to do magnitude 5s to 5.5s or 5
Yeah,
to 6
okay.
and then 6 and larger. It's all going to be, I might use 5s and larger and then maybe
Yeah,
6
okay.
and larger, but I'm not trying to really break
Break
it
it
down,
down.
or you run out of stuff to work with.
So in that specific case, then the alternatives you will consider is the normal faulting, the strike slip, right? And then you will do this exercise separately for the weights. Is that
Right, so-
correct?
So right now, think of this as just a normal faulting problem. Okay, so our data sets that we will look at, we have NGA West plus the different subsets of that were used by the developers. So
Yes.
this is one.
Was-
Okay,
yeah.
so we could have 4 or 5 of those, right?
Mhm.
Then the other one is the European data set,
Okay.
which has some differences. Now you're actually getting a little bit of independence, not a whole lot, but some, okay? And so then we would have those models. So we could have the resource data set and the ACAR data set as different subsets or collected values. Now I want to see if I run through all of those in this kind of an approach, do I move my map around? Or do I say, oh, it's consistent between those? Really, that's going to start to affect my weights on the models.
Yeah.
Okay?
And now you do this now for normal, and you repeat the same exercise for strike slip since it's important for you. Will you, or?
Yeah, well,
Okay,
for strike, so
new
if we
models.
have to build a model for strike slip, we will either do it twice,
Okay.
or
refit.
we will do one model for both.
Ah.
Okay?
Okay.
Because normal is probably going to be the dominant mechanism, I think we want to pay attention to normal by itself, and then also check those models against the strike slip data.
Makes
Okay, That's
sense.
another way to do it.
So Norm, but in the end, I mean, when you had those 10 models that were going to go into that logic tree, you might just choose 10 points out of this map, not necessarily those that are located with the red dots, but just 10 other points, correct?
Correct.
And it's just a matter of which 10 points, in other words, how far out in those ellipses are you going to go?
That's so think of this as a point we would say I've broken it into 11, not 10, but it's 11 regions, and now I want to find a representative model within each one of these.
Okay.
So
okay.
it's like any continuous distribution, I'm just discretizing it.
Right.
Okay, into a manageable set. I could pick one of those here. I don't have any to work with, so I'm going to pick one of my 1,000.
Right.
Here I could say, you know what, I could either pick this one here that's right in the center, or BSSA, I'll keep it, okay? The other alternative we've heard people say is pick one generated model in each one, and then if there's a representative published model, maintain that one, and we will probably run those separately for comparisons to make sure we haven't lost something.
Okay, I want to be clear again, then let's suppose we're looking at BSSA right there for a moment. Is that one that has been in fact transformed into the uniform functional form, or is that the actual functional form used by BSSA?
That's the actual form, as Nico has said.
Okay.
So the transform one isn't very different as what we saw the other
Right, exactly.
yesterday.
We saw very small
Right,
differences.
but
so-
there are differences.
Okay.
Norm, I suppose in each of these subregions, it would be possible to look at the amount of change of each of the fitting parameters in the common functional form, and that could be used as a criteria for either keeping a subregion intact or maybe dividing it in two. You know, so in other words, if you have a region where the total range and parameters, just to put a number out, is 0 to 1, but then you have another one that goes from, say, 1 to 3, maybe you'd want to try to have uniformity in the range of parameters.
The way I would like to do this is to be looking at some samples as I go across here in hazard space then. Okay, because the idea is we're assuming now in these are all going to have a similar impact on the hazard. but that needs to be demonstrated as we're lumping them together for that with that intended use. So that's one way instead of the parameters, I think it would be better to just run a set of them for the simple case, not running everything, and then we can reduce it later on to say, yeah, these are all in a small enough range in the hazard, I can take one and represent that value. Bob? The 1,000 hazard runs they're in sensitivity, they're inevitable, okay, but down the line we need to simplify them to, yeah. So.
You can certainly run 1,000 simplified hazards.
Correct. Yeah. That's the way we would do it. So the simplified models to help us see, are we grouping things in a way that makes sense?
Representing the zone with some, very approximate average properties and capture the magnitude range, and then we can just see what this ground motion model do across that.
Similar to what Melanie was just doing, running a very simple host zone and saying, let's see how things change for that. Ken?
I thought yesterday, sort of your grid there, you had plotted that over all 1,000 models to sort of help inform you on how to do that. Here, you don't seem to be doing it unless you did that, but you're just not showing the 1,000 models. Did I misunderstand what was being done yesterday?
No, the points just aren't plotted here,
okay.
But they were there, and also the center point isn't shown.
Right.
Okay. Part of it,
I know it makes for a busy plot, but what Yusuf said was, maybe you should make it longer, but I thought that those 1,000... Oh, your phone is ringing. Uh-oh, the wrong phone.
Sorry, I get about one call a week, so that's pretty unusual. All right. Where were we, Ken? I'm sorry.
So I was asking whether you'd use the 1,000 points mapped onto this to inform how you develop sort of your preliminary grid here.
So part of this is where should we be starting? And right now, if I put the 1,000 and the big black dot at the center, that's uniform equal weight to all of the models. So if we just start to look at it this way, we have a clean slate, all right? Where should you be centered? All right, that's the first question I had to ask. So one was the shape. Now where do I center that shape? Do I center it on the average of the 6? Do I really say, no, these European models have the most normal faulting data. Should I be going that direction? Or should I be saying I want to capture something, more in the middle here? Right now, I've moved a little bit more up towards that direction here in this model. I picked up the European models sort of in my closer range. I've kind of made an ellipse that is almost, other than CY014 in the middle, with the old models almost sort of surrounding it in that range, okay? But the part of it is what's going to be important? How am I going to then assign weights to these as I go one direction versus the other? I think if anything, I'm more likely to go this direction, right, from these models, as opposed to over here. Remember over there, I'm falling off the likelihood cliff, right? So here I go crashing off of this for that subset of the data. We want to look at other subsets to see if this cliff is a robust feature or not. But it allows more going that direction. Going that direction is overriding some of the modeling or assumptions that the people put into building their GMPE. but you're going towards the direction of where the European models are for normal faulting. Okay, so my interpretation of this is I would give a skewed distribution with more weight on this side than I would be putting on that side over there. Christine.
So to simplify, I guess you will start with the potential grid like this. You're going to look at the likelihood. You're going to repeat with other data sets spanning the same space, and then find something that seems to cover the range that you're after.
Right, and it becomes subjective at that point.
Yeah,
There's
but the
no-
likelihood is important in guiding your
to the extent that you want the data to control the answer.
yeah, to the
okay?
extent you trust your data.
And that's a big if.
Yes.
All I would say is here the data are allowing more movement in one direction than the other. Okay, so I could still, in this case, even say I'm going to center on these models here, and I'm just going to have a skewed distribution, asymmetric, a little wider this way than that way.
And by looking at different data sets, you hope
You'll
to
see
get
if that's
a better
robust or if
picture.
it's completely different, right?
Yes. Okay, thanks.
Norm, this is Robin. Can I ask a question?
Yes.
Yes. Go back to the cartwheel plot, please. I assume if you plotted, instead of event term, if you plotted the magnitude term, you would get different contours in the background.
Yes.
And I assume that you would plot a different cartwheel on top of that. So which one do you use to pick the, say, 13 out of 1,000 points to represent the whole distribution?
So one direction. You need to mute. So part of the reason for not elongating these even more is I want to capture changes in magnitude or distance scaling that might be happening as I'm going up and down vertically. Okay? But we really would be keeping these things, I think, fundamentally, Robin, we're trying to capture first order the style of the constant factor and what the shift is. The next thing is what are the magnitude and the distance scaling. Those are just different directions on this plot. So I would say right now I've elongated it, not just in the median ground motion term, but it's elongated in the likelihood term. So that has everything in it in terms of magnitude and distance scaling. So I think we're justified to be using something where my shapes are elongated in the y direction as opposed to the x direction.
Unmuted. Okay, but I would assume from this plot that you ought to have a ground motion model near the very top and near the very bottom because those are equally likely. Is that right?
That the data allow them. Now we're at the point of our interpretation of what is acceptable. Because some of those may end up with magnitude scaling that's going down and then back up, or some more complex features, or things that we would say are not likely from a physical standpoint. So when we get to the edges, other stuff could happen. But I think in general, yes, this is telling you the edges here are permissible, you could say, at least from this data analysis.
Unmuted. Okay, thanks.
All right. Okay, I have 5 minutes left. Okay, so and not a lot to add, so that's good. So for 2 seconds, the picture looks very similar. We already had a preview of this, right? So we're close to the zero line here. The models are lining up in a pretty tight line. We're getting elongation in this direction again, so that would be differences in magnitude and distance scaling going on. If I'm looking at the likelihood, the same kind of a shape, but now they're more in the center, right? So instead of using a skewed distribution and saying, I'm going to put more weight on this side than on that side, I would probably be going towards a symmetric weighting as I'm going out from this subset of the data. And it needs to be repeated for several subsets to see how robust those conclusions are. And excluding the, what Yusuf said, excluding the strange models or unphysical models that come out of the simply sampling of the coefficient distribution.
So it's probably obvious, but the key here is really to constrain those correlations and how those coefficients are allowed to move, because it's going to change the shape of the map quite a bit. And do you plan to do that beforehand by constraining what is possible in the distribution, or after the fact and removing stuff that doesn't make sense? Nico?
I would say yes, one of those two. Do you have anything more to add to that, Nico? No, okay. We haven't
But that's
found
the
an
critical
optimal
part.
way.
The
What we
rest
want to
makes
be,
sense. Right?
the key issue here is as we throw models out, we want to be sure that the mean of our recovered models is still in the right place. Okay, that we haven't got now the whole thing skewed to one side.
So that seems to push you towards doing it beforehand and constraining.
That would be better.
Yeah. Okay.
And
Thanks.
I think Brian has already indicated to us it can be done better, and so you don't have to throw models out.